So we're going to talk about log equations in this video. So when you're dealing with a log equation, or exponential equations that require logs to solve, so previously we were solving these by, if we had something like 3 to the power of x equals 27 to the 2x plus 1 or whatever, we could solve this because we recognize 27 is actually just a power of 3, and we were able to rewrite these equations as something like this. But in this case of number 1 here, where I have 5 times 3 to the 2x minus 1 equals 20, I don't really have that option, because 20 isn't a perfect power of 3. But we now know of this operation called a log that allows me to solve for what an exponent is. So the first step in here, though, is I need to divide by 5 so that I have the exponential part by itself. So I have 3 to the 2x minus 1 equals 4. So now at this point, I need to do something that will get the exponent down from the exponent and then get rid of this 3 to the power of. So we know the inverse operation of a log is an exponential. So there's 2 ways to think about what I'm about to do. One of them is, the definition of a log is that if you have log of x equals y, then that means b to the power of y is x. That's just the definition of log. And this goes both ways. So currently I have it in this form, so I can convert it to this form. So I have 3 to the 2x minus 1 equals 4, so that means log base 3 of 4 equals 2x minus 1, right? Because this was my y, this whole thing was my x, and then this is my base. So b is 3, and then this, we don't really want to say x is 2x minus 1, but that's kind of just where these things fall in this little formula, right? So the other way to look at this same sort of problem is I have 3 to the 2x minus 1 equals 4. And I'm always allowed to do the same operation to both sides of the equation. So I could say, well, what if I took log base 3 of both sides of the equation? You can see, like, we got log base 3 of 4, log base 3 of 4. So it's the same thing. It's just kind of 2 ways to explain it. So because this is now an exponent inside of a log, I'm allowed to bring it down. And then I have 2x minus 1 times log base 3 of 3 equals log base 3 of 4. And log base 3 of 3 is asking 3 raised to what exponent makes 3? And the answer to that would be 1 times 1 equals log base 3 of 4. So either way, you end up with the equation 2x minus 1 equals log base 3 of 4. Now at this point, you might be tempted to grab a calculator and calculate log base 3 of 4, but this is going to equal some sort of irrational decimal that we don't really want, because then we have a less exact answer. So I'm just going to leave this number as log base 3 of 4. And I write the 4 in parentheses because then I remember that I can't add 1 to it unless I take the log of it first. So it's log base 3 of 4 plus 1 equals 2, x, and then I divide both sides by 2, and I get x equals log base 3 of 4 plus 1 all over 2. And then this is my exact answer. As a decimal, I bet this would equal something close to a little bit more than 1, right? Because log base 3 of 4 is going to be a little bit more than 1, and then 1 plus 1 would be a little bit more than 2, and then 2 over 2, a little bit more than 1. But this is my exact, no rounding answer. Okay. In this second problem, I have logs with different bases, or I have exponents with different bases on both sides. So in this example, I'm going to resort more to kind of this method on the right instead of this one on the left, because there's, like, I picked log base 3 here, because I knew that log base 3 of 3 was going to give me 1. But since I have different bases on both sides, the easiest thing to do here is just use common log, which is base 10. And that's the one where we don't write the base. So I'm going to take the common log of both sides. So I get log of 4 to the x plus 1 equals log of 7 to the 2x. So now I can use my power property and bring both of these exponents down. And now I have x plus 1 times log 4 equals 2x times log 7. So now the goal here is to get x by itself, right? I know I have it solved when I have x equals something. So if I have x plus 1 times log 4, remember log 4 is just a number. So I can distribute this number to both x and 1. So I get x log 4 plus 1 log 4 equals 2x log 7. So now I'm just going to move all of my x terms to one side. So I'm going to subtract x log 4 from both sides, because I want all of the x's on one side and then all of the other numbers on the other side. And I get log of 4 equals 2x log 7 minus x log 4. So these aren't like terms. This is log 7, this is log 4. So I absolutely cannot combine those and make something like 1x log 3. No, don't do that. No, bad. Sadness. Right? Doesn't work. They don't equal each other. What I can do, though, is factor out an x. Since both of these terms have an x, I can bring that x out to the front, and I have x times 2 log 7 minus log 4. And from here, I know 2 log 7 minus log 4 is just a number, and because it's just a number, I can divide it out of the equation. So I will do that. I'm going to divide both sides by 2 log 7 minus log 4. So this side, the whole thing divides to 1, and I get x equals log 4. That looks weird. Log 4 divided by 2 log 7 minus log 4. Now that's an ugly looking answer. We did get x by itself. We don't have any variables on the right side of the equation. These are all just numbers that I could compute the value of if I needed to. But this is our final simplified answer. So now we have log equations. So these were exponential equations that we used logs to solve. Now we're going to look at a couple of log equations where the log is only on one side of the equation. So just like with the exponential example, there's two ways you can kind of look at the first step here. First of all, we do want to make sure we have a log isolated on one side. So if I had like a 2 in front, I would want to divide, or if I had like a plus 7, I'd want to subtract. Okay. So, again, think back to the definition of log. So we have log base b of x equals y, and b to the y equals x. So you're always allowed to rearrange from log form to exponential form. So one way to look at this is to say I have 3 to the second power equals 2x minus 3, which is 9 equals 2x minus 3. The other way to look at it is say I'm going to do the inverse operation to both sides. And in the case of log base 3, the inverse operation would be 3 to the power of. So just looking at this equation a different way, I can say 3 to the power of log base 3 2x minus 3 equals 3 to the power of 2. So I just rewrote both sides of this equation, but now it's 3 to the power of both sides, which I'm allowed to do because I did the same thing to both sides. So we did the inverse to both sides. Or we just converted to exponential form. And you can see how they're going to be equivalent things. Because 3 to the power of log base 3 of something is just going to equal 2x minus 3. Just like in the warm-up the other day, we had 5 to the log 5, 126, and that equals 126, because you're raising an exponent to the power of a log with the same base. So that's the whole definition of log. They're inverses of exponentials. So this side of the equation, the 3 and the log base 3 are inverses, so they cancel each other out, and we get 2x minus 3 equals 9. All right, same thing. I guess we ended up with 9 on one side instead of the other side, but it's the same thing. So now we, regardless of which way you like doing it better, we would then add 3 to both sides, and then x is 6. So in example 4 here, I have 2 logs on the left side, and I want to only have 1 log on the left side. So we're going to use log properties first. So if I'm adding 2 logs together, I am allowed to multiply their inputs and combine them into 1 log. So this is the same as log of x times x minus 3 equals 1. Now remember, this is log base 10 because it's not written, so this is a common log. Common log base 10. So, and notice I use the brackets here because I want to make sure I'm multiplying x by x minus 3, not just x by one of those things. It has to distribute to both. So you can do it the convert to exponential form way, or you can do the inverse to both sides. But either way, you'll end up with 10 to the first power equals x times x minus 3. And 10 to the first power is 10. But now I can see that in order to solve this, I'm going to have a quadratic, because I have x times x minus 3. So I need to distribute x, and then set it equal to 0. So now I have 0 equals x squared minus 3x minus 10, which I can then factor into x minus 5 times x plus 2, which gives me solutions of 5 and negative 2. But if I go and I plug those back in, so the 5 is going to work because I have log of 5 minus 3 plus log of 5. 5 minus 3 is 2. So then I have log 2 plus log 5. Does that equal 1? Yes, it does, because 5 times 2 is 10, and log 10 is 1. So that works. But the second one, I have log of negative 2 minus 3 plus log negative 2. Log of negative 2 or negative 5 is undefined. So you can't do the log of a negative. So this is an extraneous solution. So when you have these log equations, you do have to go back and check that the solutions you got don't require you to take the logarithm of a negative number, because that doesn't work. Okay, and then our last 2 examples, now we have logs on both sides of the equation. So with these, again, we do need to isolate the logs as much as possible. So if I have 2 times log of x plus 1, I if I try to divide both sides by 2, then I just have log base 5 2x over 2 on the right side, which still doesn't work. So instead, I can make this 2 an exponent. So now I have log base 5 of x plus 1 squared equals log base 5 of 2x. So now when I do the inverse operation to both sides, so now I can make both sides to the power of log base 5 2x. Just like in the warm-up, 5 to the power of log 5 on both sides. Those are inverses, so they cancel each other out, and we just end up with x plus 1 squared equals 2x. And of course, x plus 1 squared means I have x squared plus 1. Okay, at this point I hope you said to yourself, no it doesn't, Mr. Trenfield. X plus 1 squared is x plus 1 times x plus 1. I hope you said that, right? And then x plus 1 times x plus 1 is x squared plus 2x plus 1. 2x. Now I see I have a quadratic again, but my 2x is going to conveniently go to 0 on both sides. And I get x squared equals negative 1, and x is plus or minus I. But we don't actually we only care about real solutions unless we're working with polynomials. We don't want those complex solutions with log equations. So this equation would just have no solution. No real solutions. Alright, and then the last one we have is log of x plus 2 minus log base 4 of x equals log base 4 of 3. And again, we're going to use log properties to get one log on each side. So if I have x plus 2 minus x, I can rewrite this as log of x plus 2 divided by x equals log 3. So this is my subtraction property. Subtraction or quotient property of logs. And now that I have one log on both sides, I can go ahead and make both sides for the power of, and that's going to make my logs go away, and then I get x plus 2 divided by x equals 3. And then multiply both sides by x. So x plus 2 equals 3x. And then 2 equals 2x, and x equals 1. And then just to check, so I need to make sure that I don't have to take the log of a negative, but I get, so 1 plus 2, and then that's 1, and log of 3 minus log of 1 would equal log of 3. Log of 1 is 0. Okay, so in summary, when we have equations with logs, we have to isolate the logs on both sides, or at least on one side or both sides. So we need to have at most one log on each side of the equation. So if it has one log, we need to isolate it. If it has two logs, we need to make sure that we don't have a coefficient or like two logs subtracted or added. And then a lot of times these require log properties.